Hi students, today we are going to discuss about the dielectrics and polarization. So first we are going to start with what is meant by dielectrics. So the dielectric material is nothing but an insulator. Initially it's an insulator. So if you are applying some amount of energy to the system, some charges will be created. So now today we are going to discuss about, because of the applied external electric field, how my conductor behaves. Because of the applied external electric field, how my dielectric material, it's nothing but an insulator, it behaves. So we are going to discuss about these two. So first I am going to start with a conductor. So I have a conductor. Conductor means initially we have a free charges. So I have a conductor. If I apply some external electric field, I can simply write my external electric field to be E naught. So in this arrow mark, the length of the tail, which is tells about the magnitude, the arrow tells about the direction. So this is my applied external electric field. Because of this applied external electric field, this is said to be positive, this is going to be a negative because of the property of electric field always starts from positive and end with your negative. So because of this applied external electric field, so the positive charges in this conductor, it's moving towards this direction. Oh sorry, these negative charges are attracted toward this positive terminal, positive side, and the negative, the positive charges attracted by this negative charges. So then all the charges will be, all the positive charges will deposited in this side, all the negative charges is attracted by this positive charge. So this is called the charge density. It's nothing but your surface charge density. So I can simply write this is going to be plus sigma free. Free means is a surface charge density due to the free charges, because in the conductor we have a number of free charges. So here this side is going to be minus sigma free charges. So sigma here stands for the surface charge density, the charge per unit area. So because of this charge configuration, the electric field produced inside the material. So here my electric field produced inside the material exactly in the opposite direction of the external field. So this is a vector quantity. So my electric field inside the material is exactly in the opposite direction of the outside electric field. If we take the net electric field inside the material, so the net electric field inside the material, the net electric field inside the conductor, I may write my E net. It's going to be what? E naught plus of minus E in is going to be 0. So the net electric field inside the conductor is going to be 0. Why it is 0? Because my electric field produced by the free charges is exactly in the opposite direction but equal in magnitude. So if you are applying my external electric field, there is a same amount of electric field produced inside the material also. So the net electric field inside the conductor is going to be 0. Next we are going to discuss about the dielectric materials. Dielectrics is an insulator. Then what is the difference between the insulator and the dielectrics? See, all the dielectric metals are insulators. Okay. What is the difference? So insulators, the amount of energy required to produce the free charges is very large. In the case of dielectrics, we have to apply some small amount of energy to create the free charges. So that's why it's called dielectric materials. So in this case, I am going to take a dielectric material. I am going to apply my external electric field E naught vector. This is my positive, this is negative. So because of this applied external electric field, there will be a creation of the free charges, because initially there is no free charge. Okay, so initially there is no free charges. So initially there is no electric field created inside the material. So what's happening? After some time t, there will be a creation of free charges. Then the creation of free, after that creation of free charges, that's a alignment of the free charges. So all the negative charges aligned in this direction because this is attracted by this positive charge. All the positive charges attracted by this negative charge aligned here. But this is the charge configuration, it's not because of the free charges. This is because that initially there is no free charge. So I can simply write this is called sigma P. What does P stands for? So my P stands for polarization. I'll teach you in the next session. So what is meant by P? It's called sigma P. It stands for polarization. This is a charge, is a surface charge density due to polarization. So this is the surface charge density due to polarization. But the beauty here, the electric field produced inside is E in vector. The magnitude of the electric field produced inside, this charge is not equal to this charge. Here this is produced, but this is because of the free charges. This is because of the polarization, because initially there is no free charges. Because some amount of is spent to remove the electron from the valence band. Because of that, the free charges is created. So this electric field is not equal to this electric field. So my net electric field inside this dielectric material am I right? E net vector equals to E naught plus of minus E in, but the beauty here, this magnitude is less than this magnitude, so this is not going to be a 0. So my net electric field inside the material is not going to be 0. So if there is net electric field is not going to be 0, what happened? What happened to my remaining energy? Because initially we are doing some work to remove the electron from the valence to the conduction process. I can simply say, I'm not going to confuse with your conductor. So initially we are spending some amount of energy to the system. What happened to this energy? So this energy is stored inside the material. In the case we are applying some energy, some amount of electric field, we are getting the same response from the conductor. So the net electric field inside the material is going to be 0. But in this case, my net electric field is not going to be 0. So if my net electric field is not going to be 0, what's happening? My remaining energy, the remaining energy is stored inside the material. So from this concept, I am coming to the conclusion, I can use my dielectric material to store energy, in the case of electrostatic energy. Okay, so I can use the dielectric material to store the electrostatic energy here. So because even if you are, because of that, after some, if you are removing this electric field, there will be some finite energy stored in the system. So my net electric field inside the material is not going to be 0. So okay, so till this point no issues. So I am coming to the conclusion, my dielectric material, we can store energy into the material. So then if you want to understand what kind of dielectric material is preferable, to understand this we are going to the atomic level. So first we are going to tell you, we are going to discuss about polar molecules and non-polar molecules. What is meant by polar? Listen carefully. We know what is meant by dipole moment. So it's a dipole moment is always flow from minus to positive charge to negative charge. So if there is an intrinsic dipole moment, then it's going to be a polar molecule. If there is no intrinsic dipole moment, then it's called a non-polar molecule. So I'll explain here. See why we are going to study about the dipole and polar and non-polar molecules, to understand the dielectric material in the atomic level. So first I am going to start with the polar molecules and non-polar molecules. I will split this into two parts. So I am going to start with the non-polar. Non-polar means there is no intrinsic dipole moment. Okay. Say for example, I suppose to consider hydrogen. This is also positive and this is also positive. So there is no dipole moment. My P is going to be 0. There is no dipole moment. So, but in the case of polar molecules, I can simply take it as HCl is a perfect example. So Cl is a larger one, Cl minus H plus. So H plus Cl minus, my dipole moment is always flow from here to here. So this is called your dipole moment, is always flow from negative to positive. So in the non-polar molecules, initially there is no intrinsic dipole moment. The polar molecules, initially we have a intrinsic dipole moment. So to understand the dielectric material, we should know these things. So next, what I am going to do here, I am going to apply my electric field over polar molecule and non-polar molecule. Which molecule is preferable to store more amount of energy, we are going to discuss now. In the case of non-polar molecules, and I split this here into two parts, polar, non-polar molecule and polar molecules. So first I am going to take my non-polar molecules here. So non-polar means there is no intrinsic dipole moment, which means my positive and negative charges situated at the same point. The center of mass point of your positive and negative charges in the same line. So there is no separation. Actually, there is no separation between your positive and negative charges. So I can simply write my positive and negative. They are be here. We have positive, negative here. Okay. So in this case, there is no dipole moment when electric field is zero case. Zero case. So the net dipole moment is going to be 0, because initially there is no dipole moment at all, right? But in the case of polar molecules, we have a dipole moment. When my electric field is 0, so we have a dipole, positive and negative charge. So the dipole moment from here to here is my P1. We have a negative and positive. This is going to be P2. We have this is my positive and negative. This is my P3. P4. So we have lots of individual dipoles. So we have a intrinsic dipole in initial state itself. So when my applied external electric field is 0, my dipole is oriented in a random direction. If I take that net dipole moment, I am getting again Pi is going to be 0. It's a vector quantity. Since it's a dipole moment is a vector quantity, so all one dipole moment is oriented in this direction, one is exactly in the opposite direction. If you take the average dipole moment, in this case is also going to be 0. Individually we have dipoles, here individually we don't have a dipoles, but the net dipole moment for both the cases, polar as well as non-polar molecules, is going to be 0. So what's happening if you are applying my external electric field? So here I am going to apply my external electric field here. Because of this applied external electric field, what's happening? Initially there is no free electrons, there is no free charges, because if there is no free charges, there is no, this is my positive charges, my negative charges. So this applied external electric field is going to create some dipole moments. It's going to create the dipole moment. Because of this positive charge, what's happening? All the negative charges, it tends to move this direction. Because of this negative charges, all the positive charges tends to move in this direction. Sir, what's happening? It's going to be separate? No. There is a restoring force between the dipole, positive and negative charges. Because of the restoring force between these positive and negative charges, it beats something like this. So this negative charge is attracted by this positive charge, this positive charge is attracted by this charges. So we have a dipole moment here, for example. So this is from P1 vector, this is going to be P2 vector. So we have a n number of charges, we have a different dipoles. Actually, because of this applied external electric field, it works in two ways. One is creation of dipole moment, and then there is a alignment of the charges. So because of the external electric field, we have a two this is the work done by the external case. It creates a dipole moment as well as it will arrange the charge configuration. So what happened to my polar molecules? But in the case of polar molecules, yeah, before going to this polar molecules, I tell you all the dipoles align the same direction, right? If all the dipoles align the same direction, here my net dipole moment, it's not going to be 0. Since all the vectors align the same direction, we have a non-zero value, right? So we have a n number of individual dipoles align the same direction. We have a net dipole moment in the same direction, which is parallel to my external electric field. Okay, next, what happened to my polar molecules? In the case of polar molecules, if I apply my external electric field here, the work done by the external electric field is very, very less, because already there is an intrinsic dipole moment. So what is the work done by this external electric field is, this is just aligning the molecules. Now listen, this is my positive charge, this is my negative charge. So I can simply take here, this is going to be what? Minus plus, this is going to be minus plus, this is going to be minus plus, this is going to be minus plus. So the dipole moment produced by this is going to be P1 vector, this is going to be P2 vector, this is going to be P3 vector, this is going to be P4 vector. Listen carefully, the work done by the external electric field, it's only to align this individual dipoles. Here, the work done by the external electric field to create the dipole moment and the alignment. So, in this case also, my net dipole moment I runs from 1 to n, it's not going to be 0. The net dipole moment is not going to be 0. So my net dipole moment, because it's also in the parallel, the same direction, all the individual dipoles in the same direction. So now we have here also we have a dipole moment, it's not going to be 0, right? Here also we have a dipole moment, here also we have a dipole moment. Which material you are going to choose to store more amount of energy? I prefer non-polar molecules. Why I prefer non-polar molecules? Because here the work done by the external electric field is larger. If your work done is larger, we can store more amount of energy. In this case, the work done by the external electric field is less, because it was just only the align the molecules. So there is no work done by the molecules, the work done by the external electric field is larger. So the work done is less. If the work done is less, what's happening? The amount of energy stored inside the material is less. So if you want to store more amount of electrostatic energy inside the material, I would prefer the non-polar molecules. Okay. So now I am going to define a new quantity called polarization. I tell you, right? Sigma P. Okay. Polarization, the technical term is polarization. My polarization stands for, I can simply write the notation capital P vector. It's nothing but my net dipole moment. So here net dipole moment by unit volume. So it's nothing but my summation of P of I vector divided by volume. So the net dipole moment per unit volume, which is called a polarization. So this is also a vector and this is also a vector. So polarization is nothing but how that molecules align, right, per unit volume. Okay, sir. So in this case, my polarization vector in this direction, right, because all the dipoles are in the same direction. So my polarization vector in this direction. So here also my polarization in this direction. So my polarization is just directly proportional to my electric field. So if the external electric field gets increases, the polarization of the material also gets increases. So my polarization P vector, which is directly proportional to the external electric field. Okay. So if the external electric field gets increases, the work done gets increases. If the work done gets increases, the amount of energy stored in the material also gets increases. The alignment also gets increases. So my polarization, which is directly proportional to the applied external electric field. So it's only depending upon electric field? No. It's also depending upon the nature of the material, what kind of material you are choosing. Listen, so if I choose some material said to be X, I'm actually applying my external electric field some 5 joules, okay, 5 Newton Coulomb per inverse. So if I apply say 5, the polarization is different. If I choose the next material Y, if I'm applying the same electric field, the polarization is different. So my external electric field, so my polarization is not only depending upon external electric field, it's also depending upon the nature of the material, what kind of material I'm choosing. So if I replace this proportionality symbol by a constant, so P vector equals to chi times E. So this chi is called susceptibility of the material. So this is called susceptibility of material. This is called electric susceptibility of the material. What is meant by electric susceptibility? Electric susceptibility is nothing but the ability of the material to retain its energy stored inside, right? So this is tells about the nature of the material. So again I am telling you, a proportionality symbol, if I replace a proportionality symbol by a constant, that constant just tells about the nature and dimension of the material. Okay, so here in this case my chi E, my susceptibility of the material, just tells about the nature and the dimension of the material. In this case it's just nature of the material. So it's the ability of the material to store the energy, right? So if my P is directly proportional to my E, so we have a technical term, linear isotropic dielectrics. What is mean with that? So my electric field which is directly proportional to my polarization, right? If my polarization, the electric field increases, polarization also gets increases. When my electric field is parallel to this polarization vector, then it's called linear isotropic dielectrics. Okay, so I just stop at this point. If you have any doubt, write in the comments. I'll try to clear in the next class. So if you like this video, share it with your friends and subscribe to the channel for the more content. We'll meet the next video. Thanks for watching.